Hi there, and welcome back to Calculus 1. As you can see, I put together a makeshift classroom. You can see the Pokeball collection here. We've got a Pikachu to keep me on point. So, going ahead and picking back up where we left off before spring break, we were talking about applications of the derivative. We wrapped up by discussing something we call Newton's method. It's one of my favorite topics to discuss. The downside of that is that it's a little behind the scenes. It's extremely useful. We showed what it could do for us, but your calculator was kind of already using it, so it's a little inside baseball, so to speak. But the application that we're getting ready to take a look at from section 4.3, optimization, is probably the most important application of Calculus 1 material that you would see outside of math class. So if you've done what I asked, you've taken a look at a couple of examples that I posted into our Moodle course, one of which purely mathematical in nature. We asked you to grab a couple of numbers and make some things happen. Another application that's more along the lines of you being contracted to fence in a pasture for a farmer. So, generally speaking, when I've seen students work on this in the past, the process they use is kind of what you might call a brute force approach, or maybe a bull in a china shop approach, where they just kind of grab numbers that satisfy what we need and kind of smash them together until they find something that works. So let's take a look at that right now in the context of that example. So what we were set up with is I asked you to pick out a couple of numbers that are both positive. So I'm going to call them x, y, and they both need to be greater than 0. Their product, so when we multiply them together, we should get back 185, and we want their sum to be a minimum. So when we add them together, we want that as small as possible. So that's our setup. Like I said, most of the time what students will end up doing is they'll figure out pairs of numbers that satisfy this condition and then see what happens with the sum. So let's do that with a table. So we've got x, we've got y, and we've got the sum. So probably the easiest one to start with, well, if x is 1, the y value we would need to go with it is 185. Take those two numbers, add them together, 186. So moving things up a bit, let's see, 185 should be divisible by 5. As it turns out, the y value that goes along with that would be 37. So we add those two together, 5 plus 37 is 42. So numbers come down a bit. So that's promising. Let's keep messing around with this and see what happens. It's a bit trickier from here because we don't have any more pairs of integers that work as factors of 185. So I'm just going to kind of double things and see what happens. So if I bump x up to 10, the corresponding y value is 18.5. I promise the point's there, even if you can't quite see it. We add those two together, we get a sum of 28.5. So we're still going down. So we haven't really seemed to hit bottom just yet. Let's try to maneuver this just a little bit more. So I scale x up to 20. Y would go down to 9.25. And the sum, when we add them together, is 29.25. So looks like now we've kind of bottomed out and we're starting to climb again, right? So it's not 100% clear, though. Is this our minimum? Is the minimum between these two? Is it maybe between these two somewhere? Did it keep dropping after 10? It'd be really great if we could come up with some more concrete way to describe this, because I'm pretty sure we've all got better things to do with our time than just repeatedly taking pairs of numbers that multiply together to give us 185 and seeing what their sum is. If for no other reason, because there's an infinite number of possibilities, and you'll die before you're done. So let's see if we can get a little more concrete about this. As it turns out, I've already kind of given the game away when I wrote this word up on the board right here. So it says minimize. We're actually looking for a minimum for something. And hopefully you'll recall from what we were talking about in chapter 3 that we spent an awful lot of time there tracking down maximum and minimum values of functions. So if we come up with some sort of function, which won't be too tough, we can describe a way to find a minimum for this thing in terms of derivatives. So I'm going to start things off. I'm going to call that x plus y sum s. You don't really have to, but it makes me feel better to see that it's got a name. So that's our first move here. Now the problem is, at the moment we've got two variables floating around, x and y. Everything we've been doing in calculus tends to want to act like we've only got one variable. So it'd be great if we can find some way to take this and knock it down to where we only have one variable in play. Fortunately, the setup of the problem lets us do exactly that, because we also know that x and y have to give us a product of 185. So what I'm going to do is take that equation, defining the product of the two functions, and solve for one of the two variables. I'm going to go for y in this case. You could also go for x. Now, you might have written this as 185 divided by x, and that's fine. For reasons that will become apparent pretty quickly, I think, it's going to be more beneficial for us to have it written as x to the minus first. So once we've got this guy, we can take it and we can feed it back into this objective function right here. That's what we're going to call s going forward. Spoilers. So now s is a function of one variable, x. We'll have x plus 185x to the minus first. And now we're cooking. This is like calculus 1 type stuff. This is a thing we've seen before and we kind of know how to handle. So hopefully, as you'll remember from chapter 3, in order for a function to have a maximum or a minimum value somewhere, we have to have what we call the critical number. So at a critical number, your function's derivative is either going to be 0 or the derivative is undefined. So now let's go ahead and crank out a derivative of this thing so we can check to see where we might have critical numbers, possible candidates for this minimum. So using our derivative rules, the derivative of x is 1. Using our buddy the power rule here, the minus 1 hops out front, so we get negative 185. We subtract 1 from the exponent and go down to x to the minus second. Technically, this is undefined if x is equal to 0 because this x to the minus 2, it really lives in the bottom of a fraction. But we're not worried about x being 0 in the first place because x has to be positive to begin with. So we can just kind of ignore that for now and focus on where this thing is, in fact, equal to 0. So we can do a little algebra from here in order to figure out what has to happen as far as x is concerned. So the magic of algebra tells us that x squared has to equal 185, and then to get x by itself, we just take a square root. So x equals the square root of 185. Again, technically, when we take a square root, we've got a plus or minus thing going on here, but we've got to be positive so we can safely ignore the negative root. So, as it turns out, we've only got this one candidate. Now, it's important, though, to verify that this is, in fact, giving us a minimum. One of the fastest ways to have to go look for a new job is if your boss tells you to maximize profits and you cheerfully minimize them for him instead. It doesn't end well for anybody, really. So we want to check that we do, in fact, have a minimum right here. So let's do that. So from chapter 3, our main tool for confirming that we, in fact, did have a minimum or a maximum, and as the case may be, was sketching out what we call a sign diagram for our function's derivative. So I'm going to do that right now. I'll draw out my number line. So I got 0 right there. 0 is acting as sort of a hard cutoff for us. So, I mean, again, technically you could draw out what's on the other side, but the constraints of the problem say we don't need to worry about what's happening when x is negative. So I do like to label my diagram s prime of x. It's not strictly necessary, but I like doing it. So now remember, in each of these two parts of our number line, what we need to figure out is whether our derivative is positive or whether it's negative. So I forgot and erased my derivative. I'll sketch that back in real quick. So we got that guy right there. And you can sort of imagine this is taking some sort of test value, plugging it in here, and seeing what happens. So if I plug in, that should be a negative. That would really throw stuff off. That was a minus. So picking a good number between 0 and the square root of 185, 1 works, and it makes this calculation really easy to work out because 1 minus 185 is, in fact, quite negative. So you get a minus right here. On the other hand, once we jump past this tick mark at the square root of 185, we need to pick something kind of big. You could pick just about anything that you want that's bigger than this thing. 15 is enough. I'm just going to say a million. So then you'd have 185 divided by a million squared. That is a really tiny fraction. 1 minus a really tiny fraction is not going to be less than 0. So our derivative does in fact change sign from here to here. That's what we wanted to see happen. That does indicate that we have a minimum. So huzzah! All right. Now, the catch is we now know what x value gives us a minimum for s. It's not quite what we were asked for, though. We were asked for a pair of numbers. So not only do we need to identify what x is, we also need to identify the corresponding y value. The good news is it's not too tough to work out, because remember we had this formula that told us how to get y based on x. We used it earlier. So we've got 185 over x. So fill in our target x value, and I will spare you the heartache. That also ends up working out to give us the square root of 185. So we've got what we were after. Nice. So as it turns out, what I've walked us through here in looking at this example has basically codified this process into what you can break down as 4 steps. So if you take a look at the second handout that I have posted in Moodle, it's actually got the 4 steps of this procedure laid out. And it has another example, a bit more real world than just taking some numbers because your math teacher told you to take some numbers and make sure they did stuff. So what I'm planning to do going forward is looking at that procedure and using it to tackle some other problems. So that's where we're going to be headed next time. So stay tuned.